He's a candidate for the Cyber-Physical System Engineering faculty position here at DePaul. Umer Huzaifa. He's a faculty member, in fact, an assistant professor in the Department of Electrical and Computer Engineering at Roscommon Institute of Technology. He's completed his doctoral studies in the University of Illinois at Urbana-Champaign, and he has a bachelor's degree in electrical computing from the National Institute of Sciences and Technology in Pakistan. He has won many prestigious awards, most notably the Best Poster Paper Award at the International Conference on Biomedical Robotics and Biomechatronics. And he's also the recipient of Navy's Future Faculty Fellowship and Graduate Teaching Fellowships at the University of Illinois at Urbana-Champaign. So his main research interests are in making leg robots walk with style, right?
Yep.
It's a very intriguing research direction. So I'm, for one, very excited about learning what this research topic is. So without further ado, let's welcome Umer to talk more about his research. Thank you.
Thanks for the introduction, Saru, and thank you all for inviting me here and giving this opportunity to talk about my research. So as Saru mentioned, my research is on making robots walk, but with a style. So first, I would like to give some motivating slides on why did I choose this topic. The first motivation is the human body itself. As humans, we are very capable when we are walking in an angry mode, when we are relaxing, or when we are just acting to act as a boxer or a ballerina. There are so many things we are communicating just by our movements, and specifically our walking, the way our legs are moving. So human body is capable of communicating a lot of things just by its structure and the way the legs are moving, more specifically. The second piece of motivation is the Atlas robot from Boston Dynamics, for example, which is capable of forward rolling, the back flipping, jumping, and other routines from gymnastics. A very capable robot, and among other human-like robots that are being developed, which are focusing on mimicking humans. So this specific routine was from one of the U.S. gymnastic Olympists this year. I forgot her name, but they're trying to mimic, as I was talking to one of their employees, they're trying to literally mimic some key movements on the robot. So they're testing the capabilities of this robot in that direction. The third piece is the applicability of human-like robots in different areas. Two very specific areas are education, or giving company to kids and elders, where human-like robots are thought to make a very good connection with those people because of their human-like morphology. And if you can program them in a way that gives soothe company to elders and youngs, this will be very helpful. The second piece is one initiative by Ford and Agility Robotics, where they're trying to deliver packages using the digit robot you're seeing in green color to deliver packages. So the point I'm trying to make across is human-like robots will be useful in many different fields around us, maybe not today, but in near future. So this is a research direction and an active direction being put forward by industrialists and different government agencies. My goal is to, just like we are moving and communicating non-verbally to the human observers around us, I want the robots to be able to do that as well. Because if we want the robots to be acceptable for the people, they need to make that non-verbal connection with others, because that's an important piece of our living. As I'm moving, as I'm talking, my gestures as I'm talking, as I'm communicating, is contributing, is supplementing meaning to what I'm saying as well. So robots need to be able to non-verbally communicate with others, along with their good functional movements. So now, to my research towards that goal, there are three pieces that I will try to address in this talk. And those are, first is how to generate different walking styles, and the maths behind it can be feasibly, provably generate different walking styles. So for me, walking is just moving from point A to point B, and styles means different ways of achieving that. So this graphic, I'm literally trying to show 2 points and different pathways to achieve that. Secondly, once I have those walking styles, I don't want to come up with styles by myself. I want to include input from experts and humans to corroborate that. So that's my validation piece, where I take human perception of those walking styles. And the third piece is where I will talk about what happens as I take that to a hardware stage where I'm trying to implement them on actual hardware. And just to call out to people that wherever you're stuck, or if something is too thick or too confusing for you, do let me know, and I'll be happy to answer any questions along the way. And I will try to make sure after every section I will take a pause and make sure that people are on the page about that section at least. Okay, so first disclaimer, I'm not the only person doing walking styles per se. Especially in the community of animations, there has been quite a lot of work done on having different styles generated for androids or just some animations. So one very key contribution is from Etamad and Arya, where they have classified styles using emotive labels, so to say, where they have described some gaits to be happy, sad, neutral, masculine, and feminine. And what they've done is they've taken stick figures without using any physics behind them and generated a model that can tweak how they walk, how these stick figures walk. Then they brought in animators to let them play with that model and ask them, can you generate this kind of walking? Can you have us generate this kind of walking? Once they generated those walking styles, then they validated those from lay humans like us. And by the end, they had these different walking styles achieved. So a very impressive piece of work. The thing I will try to address as compared to them will be providing physics to such animations. I will try to bring in physics, a piece of actual dynamics in these stick figures, and say, and then investigate, can I have walking styles for that? Another very well-known work is done by Aaron Ames and their collaborators, where they have taken this off-the-shelf robot, Duris, and what their piece is, their focus is to mimic humans in different aspects. So what their focus was to focus on the toe push-off, and they tried to mimic that. And with that, they declared that now we have a human-like walking style, because that's an important contribution to your walking, how you leave the ground. So focusing on that and designing the robot that way, then designing the control algorithm that way, they achieved human-like walking. So this is an important contribution as well. The piece is, when I say human-like walking style and styles that are meaningful to people, need to involve humans, and the robot needs to have different walking styles that it can switch between in different scenarios. So that's something different from what I've been doing. And the last couple of motivations are, first is having different walking styles is not a new idea in itself as well. There have been work done on developing gait libraries. For example, in this work, you're looking at a robot model that is traversing an obstacle course. And you can notice that it's switching between different walking styles. It takes a pause for some walking steps. So what it's doing is it's switching between different walking gaits. Those walking gaits are different based on their gait speed. So what they had in mind was they had a gait library based on different walking speeds. And the robot would just switch between those different walking speeds to traverse this course. So the idea of gait library is there as well. But it's doing a good job. It's doing a difficult task. But I want walking styles that are distinguishable by people. Like, people cannot distinguish between different these walking styles, or these walking styles are not distinguishable based on their quality. They're just distinguishable based on their different walking speeds they have. Yes?
I'm sorry, so what was the source of their gaits here?
Their gaits are...
Is it a model, or is it from...
It's a model. They have developed a mathematical model of this. And then they had designed gaits that can switch between, that the robot can switch between. for this goal of traversing this obstacle course. Again, my difference for this was I'm working on a set of gait styles that are, even if they're not functionally different, they're visually different. So people can distinguish and relate those to different experiences. And now towards what I want to do is, since I want to mimic humans in some sense of developing different walking styles, it's good to go back to how biomechanics and people who have studied human body, let them say how humans actually walk. And from this very seminal paper from 1950s, one of the authors related, and this is an established finding in biomechanics, is that in walking there are 6 main determinants of gait. And among the obvious ones like leg lifting and knee bending, there is an important contribution of your pelvis. And that's a region above your legs in your stomach area where you have your pectoral muscles. They have an important contribution. And more specifically, they noted 3 different movements of pelvis that give you walking. The one is this lateral displacement of pelvis, and the other 2 are 2 rotations in different axes when you're walking. So what they're pointing out is, even though you're not noticing it yourself, when you're walking, along with your leg lifting, there is a movement happening in your pelvis. So coming across this, our idea was to, since we want to generate walking styles, how about we simulate this pelvis in the robot and then tweak the proportions of these 3 movements to come up with different walking styles. So using the movements of pelvis and tweak their proportions, we wanted to have different walking styles. Now for that goal in itself, we started very low, and we first saw how about we first model one movement of pelvis and try to model that. So before going into the details here, let's first look at what's happening to the left. I'm trying to abstract out a human's thigh and pelvis with this model. And what this model is saying is, I have 2 stick figure legs, where I'm assuming the legs are just straight lines and they have their center of mass at the center. And in place of pelvis, and it's very complicated movement as I just described, I'm just focusing on, the forwards and backwards movement of the pelvis. Because as you're walking and it's rotating, pelvis is rotating about 2 axes, along with the lateral displacement, it is moving forwards and backwards as well. So for a mathematical model, I started very low to have very provable set of walking styles. I started with this walking style. I started with this model, where I'm focusing on just 2 legs and a pelvis mass that can only move forwards and backwards. Okay? And for the rest of the 2 slides, I will go into some maths of how do I model it and how can I define equations of motion for this structure. Or in simpler language, what I want to do is, if I provide forces and torques in this robot, how will the legs move? Just like a car, a mathematical model for a car is, if I press the accelerator, how much distance will it cover? So I will try to mathematically model this. So if you zone out for a bit, don't worry. I will come back and connect it to the rest of the talk. Now, the way I model this is a robot, and it's supposed to walk. Now, even though we don't notice it ourselves, when we have to define walking for a robot, we have to be very specific what's going on. So first thing is, we can define walking in 2 phases. The first phase is where one of your legs is grounded, and the other leg can be swung till it reaches the ground. We call that a swing phase. Again, when one of the legs is grounded, and the other leg, the swing leg, can move and reach forward. In the swing phase, we have a very general mechanical structure, which we can model using Euler-Lagrange modeling equations. So what you're looking at here is an equation of motion that just tells you if you apply this much force in the robot, you will have this much acceleration and you will move forward. So this equation of motion is only talking about this first phase, swing phase, where one of the legs is grounded and the other leg can move forward. Okay, so by the end of this phase, you will have an equation in motion relating how much force you apply and how much acceleration and the positions you will get out of it. Now, the second piece of modeling is,
Sorry.
yes.
Question? Do you mind going back?
Sure.
Is there an intuition why QS and QS prime have the same coefficient, but the second derivative is different?
You're saying, are these coefficients different? DS, CS, are they different coefficients?
No, I'm saying, so you have, why do you have QS and QS prime grouped together with the same coefficient CS, but the second
Okay, that's,
derivative is
okay. The reason I've done that is the CS matrix is made up of QS and QS dot. The terms inside this matrix are functions of QS and QS dot. That's why they are. I cannot share more details in the slides, but I can definitely show you what this looks like. I try to be as concise and as keeping it as watered down as possible, but for now, I would just say that this is a set of equations in motion that describes what happens as you apply the force on the robot, what will be the accelerations from the robot. Now, the second piece of this modeling is, as your leg is swinging, it has to reach the ground at some point. Because you're swinging, for taking the next step, you have to make it reach the ground. In that point, our main focus is, as that contact is happening, that contact is actually between two mechanical bodies. So it has to be nice and smooth. It has to satisfy some conditions. So among other conditions, we enforce that there's no slipping happening. Our main concern is when the robot is walking, it should not slip after each step because it's a contact. It should not be as bouncy as I drop a ball or anything and it bounces off. We don't want that. So we don't want slippage or any bouncing back. So those are the two things I just want you to remember. And for this phase where the leg reaches the ground, the name for that phase is strike phase. And the way I model this is, just for the interest of this audience, what I'm trying to do is, I'm trying to implement this condition that there is no slip or rebound. And the way I implement that is, I first find the velocity of my swing foot that has just landed on the ground. And I'm saying the velocity of that point in the horizontal direction and the vertical direction. Horizontal direction is my slippage. Vertical direction is my bouncing back. I'm just making sure that this is staying on the ground. There's no slippage or no rebounding happening. The way to make sure that is, I call the velocity to be equal to 0. And again, by the end of this phase, what I want is, I want to know if I landed on the ground with so-and-so joint angle for my legs. After that, I should know what my next joint angles should be. So the goal of this phase is to know, going into the strike phase or going into this striking with the ground, I should know what is my joint angle going to be as I take the next step. Okay, so again, overall view of these two slides was to mathematically model the robot. And sorry, I had to go into the details of Euler-Lagrange modeling. But what we really wanted to do was, given some forces to the robot, what will happen to the position? And from the perspective of walking, how would we model it? We saw that we would model it with first one swing leg moving, and then it reaching on the ground, and both legs being on the ground. So just mathematically describing what happens as I apply forces to the robot, this is what the mathematical model will be. Now, that's all about what happens as you apply the forces and what happens to the joint angles. The next piece is, we want to know that unique set of forces and torques that can give me walking. So I want the robot to have a stable walk like this. Among other things, as no slipping, no rebounding, it should have a continuous walk for multiple steps. Now for that goal, I need to find that golden or that super unique or super good input forces and input torques that can help me achieve that. Now for that goal, I have to do some other work, which I will explain in these two slides. first step is, since I want to have multiple walking styles, I define some gait parameters. Now these gait parameters are some values which I change to have different walking styles. These are hand-picked gait parameters. First gait parameter is just the movement profile of the top mass. This top mass, again, to recall, is a simulated pelvis that only moves forwards and backwards. I'm assigning some waveforms to that, saying if it moves in these movement profiles, does it change the walking profile or not? So just by movement of this mass in these profiles, can I have different walking styles? Along with that, I'm saying if I change the step length, meaning if I change how far you step forward, does that give you different walking styles or not? So I'm calling these two the pelvic shift and thigh lift. I'm calling these my gait parameters, and for different values of these two parameters, I will investigate if I can have different walking styles. Okay? And again, for the goal of finding that unique or that super nice input torque and force that can give me walking, I will apply the method of feasibility problem. So what that is saying is, I formulate this problem as an optimization problem. And this is a special type of optimization problem because what I'm saying is I'm not minimizing any function. I'm just saying, given so-and-so constraints of walking, just find me any input that satisfies that. So again, with the mathematical model I had, I'm trying to find an input that can give me walking. And based on the values of pelvic shift, PS, and thigh lift, I want to have different walking styles. The way to find that is through a feasibility problem formulation, where I just say, find me an input that can satisfy the constraints of walking. And what are the constraints? The constraints are, whatever input you get, it should satisfy the dynamics of the robot, meaning it should not break the robot. The forces should not be too much that the robot breaks away. The second is, it should satisfy the periodicity. Like, it should not be good for just one step. It should let the robot move on and on and on. And then you have the constraints of the gait parameters we just chose. We want to have that input that allows the mass to move in that specific profile. And also, it should satisfy the step length we chose. Now, for different values of these TL and PS, we will have different inputs and hopefully different walking styles. So apart from the maths behind feasibility problem, does everyone understand the goal here? Why we're doing what we're doing? We know how the robot moves. We want to know the specific input that makes it walk. We just don't want it to move. We want it to walk. And for making it walk, we have to define some constraints, how the walking happens. And in those constraints, we want to include some gait features saying that the mass should move this way, and the step length should be any of the values I give. Okay?
So this is the internal.
It is not.
It's not?
It's not.
Okay.
It's I have modeled it as it is. Inverted pendulum model says they model the human body as a single mass that is just moving in an inverted pendulum. I'm considering that as it is. I'm not making any assumption. I'm just saying that it is the model at itself.
So where do the masses go here?
Where is the?
So you have masses for the legs, right?
Yes.
So these legs are
Inverted. Sorry, just to connect. Inverted pendulum just has one mass on top.
Yeah, yeah. So,
That's very
so
different.
You see some distributed mass, right, in the legs.
And I do consider lumped mass
Lumped
at the
masses,
centers. Yes.
And these legs are just one rigid link.
Yes.
Okay, so they don't have knees.
They don't have it.
So you achieve the. So you have a hip.
I do have a hip.
Okay. So you see.
Yeah.
Sorry, the conversation is very strange at this point.
Sorry.
No, it's
yeah.
okay.
So this is most of the maths we did here. After that, honestly, everyone should just call me out and ask me questions on this. But yeah, after this, we will go into the styles we have and other things of interest to other people as well. So once you have the problem optimization problem formulated. For people who have background in optimization, they would know that you can find analytical solutions to some optimizations, but some optimization problems are so hard that you have to rely on computational tools. So that's what we did here. For solving this optimization problem, we relied on direct collocation method, which just says you take your input and state vector, the x of t and u of t, and instead of applying the constraints on the whole trajectory, you apply the constraints on discretized values of the state and input. So this way you make this a discretized problem instead of an analytical problem. And then you can use off-the-shelf tools from either MATLAB or we use a third-party software, GPOPS2, to solve this optimization problem. Okay, and now we have the result of walking styles. So here, among all the different walking styles that are generated, here are a sample of a few walking styles here. So what you see here is for different values of pelvic shift, or PS, and different values of step length, the thigh lift, you can have different walking styles. So this is what we were choosing. We were choosing different values of PS and TL, solving the optimization problem, and coming up with different gait styles. Okay, so what this section was about was how can we have mathematically established walking styles on the robot? How can we, or literally just moving from point A to point B, how can we move it in along different trajectories? So this is what the goal was. We went over how do we mathematically model a robot, meaning what happens is I apply some forces to the robot, how do the legs move? Then we found specific inputs that can give us different walking based on different values of PS and TL. Yes, yes, sir.
So is it, what about the stability of these?
So what we did was we established stability for one step. Here you're looking at looped animations. So we haven't established stability for multiple steps.
Basically, once you land a foot,
yeah.
So then you don't really consider the dynamic stability until you land the next step.
I do consider at that point. So what I'm saying is, I don't. Sorry, could you repeat the question again?
So yeah. So to me, it looks like if you don't use dynamic stability, right? For example, when you're on your swing phase, right? So you have one leg up, and then the dynamic stability becomes a problem, right? So do you consider the dynamic stability scenario?
I do consider that.
Okay, you do consider that.
Yep.
So what about the orbital map for these?
Orbital map for one cycle is it does become a limit cycle.
Okay.
I don't have it here, but
okay. I see. And you don't. There's no energy loss in at the impact.
There is energy loss, but what we have is conserved angular momentum.
Okay.
Yep.
So if you conserve the angular momentum, there's no loss.
There is loss because as I reach the ground, nothing is moving. Nothing is moving for that instant.
Yeah. So if you don't lose momentum, where
Yeah.
is the loss?
The loss is. I'll have to cross-check and get back to you on that.
Sure.
Yeah.
No problem.
Yes, sir.
How's the pelvis attached to the legs? I thought the pelvis was kind of the intersection of the two legs, but it seems to be moving independently of the legs somewhat, no?
It is moving independently. So what we did was we constrained the movement of the pelvis to, we constrained it to be just moving forwards and backwards. So we have a mechanism of just keeping it at its level. So it's just moving forwards and backwards. So yes, it looks independent to the masses, but it does affect the overall dynamics of the robot.
So in the eventual robot model, if you build it, what would that correspond to then, the pelvis moving independently of the legs?
It will be coupled with the legs.
Okay.
Yeah. Sorry. Okay, yes.
So for the parameters that you've got there, could you watch human gaits and extract the same parameters and then compare them to see whether they're similar to your gaits here, or do they vary too much because of other parameters?
That is one of the future goals. The problem was when we were doing the research, we were not sure what exactly should we look at, because we studied some papers on measuring the pelvic movement during walking, and the problem with motion capture is the normal motion capture suits, they do move a lot. The markers do move a lot. So what they proposed in the paper were invasive markers. So they literally drilled markers into the spine to measure the spinal movements. So it was not, we didn't want to take that route at this stage. So we just came up with some movements and saw if this was possible for made up waveforms and try to make it work. But that is a goal, to get some features from the spine or the pelvic region to guide the choice of PS, the pelvic shift.
Think very carefully when answering your call for volunteers then.
Definitely. No harm will be done to the volunteers. Okay, the second piece is, now that you have different walking styles, how do you connect the human piece to that? How do you make sure that humans perceive them to be meaningful as well? And for that, the strategy was that once you generate the gaits, we thought of bringing in a movement expert. And by movement expert, I mean people who have experience working with humans, tailoring their movements. So the collaborator we had, she had a choreography background, and she helped people in movement therapy, and people with movement problems. She helped with those. So her job was to look at the gaits, the animations we have, and pick and classify them in a very manual fashion in different categories. So she classified them using English language words. Because one point to remember is, by this point, we don't have any established mathematical definitions of different walking styles, or we don't have any qualitative definitions of walking styles to this point. So we chose English words like stagger, drag, amble, and our collaborator from movement background helped us achieve that. Once we do that, that's not enough as well. So we throw the animations out to people and ask them to verify those labels that we assigned them. And once we have some reasonably good response, we go ahead and label those gaits as a stagger and a validated stagger, a validated drag, and those labels. And if some results are not really making any sense, we go back to the generation stage. We churn some more parameters and find other gaits that make it work. So the way this works is, once you have the gaits established and once you have the gaits ready, the way we conduct a user study, or taking the input from the people, we conduct a user study that explains first what the biped model is. So we explain that they're looking at two sticks, which are actually two legs, and the robot is moving forward. And we also make sure that they're actually looking at these descriptions by taking their test along the way. Once we explain the model, we go over the words we use for different gait labels, because in normal spoken English, we don't use a lot of words for walking. We just say walk or trod or other words. But there are other words that also ascribe to different styles of walking that people are not familiar with. So we provide meanings and the sentence examples from literature so that they know what the words mean. And then we ask the rating for those gait labels. We ask them to rate them on a scale of 1 to 7. More is good. More means that the label is what the animation they're looking at is. Now for this procedure, we chose these gaits. Now you can see that stagger and amble are distinguishably different from shuffle, drag, skim, and saunter. You can note that by looking at the leg profile. Stagger is swinging much more than how the drag is moving or the shuffle. So all these labels were assigned by our collaborator movement expert. Taking these animations, we ran the user study, and these are the results we have. Now let me spend a little bit time of what you're looking at. What you're looking at is the average rating on a scale of 1 to 7 each gate got. Now you can see all the scores are above 4. If the average score were 4, it would mean that they're unsure if this is an accurate label or not too accurate. So since they're all above 4, this means that almost all the participants agreed to the labels we assigned. And they agree that these are stagger, drag, and saunter, and all those labels that we have. So this is a convincing slide that this walking styles that we generated, they do relate to, people do relate to them, and they have some promise. And if we have more realistic models, we will have walking styles that people can understand. Yes?
So how did you ask them? Did you show them the animation and then said, does this look like an amble to you? Or did you give them all the 6 options and they have to rate each one for the animation?
That's a good point. So we chose the first option. We just give them the label and said, do they agree or not? What would be another layer to that would be to ask them, which of these 6 do they agree?
So is there a danger? Remember, directors will tell you that you take a totally expressionless face and then you tell the audience what they're seeing and they read that into the face, even though the face doesn't mean anything, but it's the same face. Is there a danger?
That is a problem. So one problem that we were seeing in that is they would pick the label, or they would pick the word that they're most familiar with, which heavily biases the results. So we're not sure which is the best way, but we went with this one for a start. And
so you could try to give them all words and have them rank each one of them, like to what extent does this look like an amble or drag or saunter or shuffle? We
could do that. That could be another way of doing it. But for a start, yes, we gave them just a label and asked them if they agree to this or not. And we did the same procedure for another biped model that I haven't described here, which has 2 legs. And you see some unfamiliar terms on the other columns, but just look at the last 2 columns and see that these are all different gaits with other gait labels assigned to them from our movement expert. And using the same strategy, we got above average score as well. So what this piece is talking about, this piece of my research talk was talking about, bringing in the human input to what the gait styles are, and making judgments on if these are actually human-like walking styles or not. So this piece was talking about that. And I can take a pause here and take any more questions if you have. Okay. The last piece is, how do I take this to a hardware model? And this was our approach right from the start, when we were taking this abstraction of the pelvis and the leg to a robot. We came up with this design that was in a very crappy simulation, but the idea was that on top of the legs there should sit a mechanism that, just like a pelvis that moves in different directions, it should allow a heavy piece of ball to roll on it, and just by rolling from one end to the other, it should introduce mass shift in the 3 directions. It should have the mass shift in the forward right, then backwards, and to the forward left. So in a way, if you look at it from the top, this captures a lot of features from human pelvis. Because as humans, when we are walking, we are also shifting our mass sideways, so the pelvis mass sideways, and also forwards. Okay, so and the idea was, if you change the size of the tray, if you change the shape of the tray, this will give you different mass shifts for the ball, giving rise to different walking styles. So again, going back to the original idea, taking inspiration from pelvis, the idea was to tweak the proportions of different pelvis movements, and from that deriving different walking styles. So towards that goal, we got some collaborations in University of Tulsa, and they helped us build a tray that was sturdy enough to take a heavy ball. And what you're looking at in the middle is 2 designs of the tray that can hold a heavy ball. This, I believe, was used for bowling that they placed in there. And then they designed a mechanism that allowed the ball to move from one end to the other by just tipping the tray up and down. So just by tipping it up and down, the ball could move from one end to the other. And from that movement, they measured the forces applied on the base of that mechanism. And from that set of forces, we did some analysis. Is there any question on the inspiration and the contribution on the hardware side yet?
So that is the actual hardware.
Yes.
So you have 1 degree of freedom.
Actuated 1 degree of freedom.
Okay.
But the ball has a lot of degrees of freedom. Yeah.
Yeah. So did you do any comparison how efficient is it rather than actuating directly the joints?
Oh no, we haven't. Or actually, we are only interested in this part of how do the forces behave. But yeah, we haven't studied. To my knowledge, they haven't studied either. What is a more efficient way?
So, do you have like picture of the actual system?
Actual.
Like that one? So that's the model, right?
That's the model.
So you have a similar setup.
Not the legs. So far we just have the tray.
Okay, so what were you measuring?
We were measuring the forces because of the ball. As you move the ball,
Forces where?
forces at the base.
Basing say the joints.
At this joint, yes.
Okay, so do you have a force sensor somewhere?
Yeah, there's a force sensor at the back, at the base, at the joint, yes.
Okay. What kind of force sensor is it?
I do not have information of that, but that's a 3-axis force sensor. I don't know exactly what that is.
Okay. All right. So that's the paper that you published on
Yes.
here. Okay.
Yeah. And there's more to that. So once we measured the forces, we made a comparison with the forces we applied on the mass, and the forces. Since the force is in 3 dimensions, we looked at the force in one axis, in the forward and backward direction, and tried to make a comparison. Now, these two things are very different, of course, but what we found that, for one, that there's a massive mass shift as the ball moves from one end to the other. So we proved that, and that the force profile sits in somewhat similar envelopes. The force I apply on the mass is between -10 and 10. The one from the hardware is between +15 and -10. So it doesn't say much about the comparison. It doesn't say that the hardware is the right one, but we have some comparison and some compelling argument that this structure can introduce a force shift or center of mass shift in the forward and backward direction.
So I believe it's only applicable to limited types of walking robots because there's no way you can control the stability.
That is definitely a problem. We will see once we construct the legs, but yes, it will be a hard problem to control it.
So,
But yeah.
I'm not sure, so I'm not quite sure I understand the purpose of this. Is the purpose of this piece of hardware to help you go back to your models and to apply those? So you need that piece of hardware in all of your future robots, in order to get the right gait?
This is the hope. This is one direction that we hope that for the future robot, it should have a simulated pelvis, because pelvis in humans is providing different walking styles, according to one theory. So we want to have a robot that imitates pelvis in some sense. This is one idea in that regard. And
So why do you need to measure the forces? Is that to...
the point of that measurement was to make a claim that such a mechanism can give us forces, can give us enough mass shift so that you can have a walking style. Because the argument when we wrote the first proposal, we got the review saying this may not generate enough mass shift to allow walking. So the purpose of this activity was to make a claim that you can have a massive mass shift that can give rise to walking. So the hope is once you have a mass shift, the legs should come into play and catch you, and then take you forward. Then again a mass shift and catch you, and take you forward.
So if one had arms later on, this may not be necessary because that may introduce a mass shift instead.
If you have if you have very heavy arms, and not using them for anything else, then so yeah.
Sorry.
That's a good analogy. Okay, so for this point, for this piece of talk, I was demonstrating one approach to hardware implementation on our ideas. And again, inspiration was to have walking styles. Idea was to use some version of pelvis in the robots to achieve that, because pelvis does 3 different movements, and the hope was to change proportions of those 3 movements to have different walking styles. This is one idea, that we should have a tray with a ball, and changing the shape of the tray and changing the trajectory of the ball, we should have different walking styles. Okay, then now I will discuss some future ideas that I want to explore. First one is that for moving out of the simulations, I want to take the results to actual hardwares. Now, for taking them to actual hardwares, I need to look at actual human input, as we were talking before, that what do humans have in their pelvis going on, or what are other tweakable features in human bodies that we can pick and apply onto robots. So I will still use a trajectory optimization framework because it allows me to have solutions based on different values of my tweakable parameters. There are still questions on which features should I pick from human body, which joints should I pick, should I actually drill markers to spines, or not. And this implementation can be done to exoskeletons, prosthetic devices, or actual robot hardwares. So the one on the left you're seeing is the Duris hardware, Duris robot. And in there, I'm hopeful of starting collaboration with and approaching biomechanists as well, and take their input on what do they want in their prosthetic devices. How can we improve the personalization of prosthetic devices to the patients? And the second piece is to include the effect of environment and the context, because we want different walking styles, but the robot should be capable of switching between them based on environmental cues. It shouldn't be thumping its feet around in a party. It shouldn't be making a noise in a home. So it should have a decent walking style based on the context it has. The questions are, how do we extract information from the environment? Is that just a background image? Is that the color of the environment, light color? And again, the end goal is to take those learning to actual hardware robots or prosthetic devices. In this one, we have one contribution already made in a conference last year that implemented those animations on different backgrounds. And we saw that by changing the background, people's opinions change altogether. So even for this user study design of picking one label and rating them on a scale, that also went all over the place just by changing the background. So that, in a way, proved that including the background and carefully tweaking them will be necessary to come up with a walking style. And the third one is that instead of just hand-picking the waveforms for my pelvis, I want to approach it in a more systematic way. One idea is to make a Fourier series equation out of it, and then look at the parameters AI, BI, and A0, and look at the ranges of those parameters to formally say that for these ranges of these parameters, we will have these so-and-so walking styles. And in that, I'm hoping to have some machine learning collaborations where we can have some formal classifications of parameters and have results in that direction. And the last is to keep working on this hardware work, where I want to go back and forth between the design iterations and the simulations to potentially have a final hardware bipedal platform. So finally, what I want you guys to leave with is robots are doing amazing. They're progressing. They're making better robots are coming every day. But to make them acceptable to people, they need to know the nuances of movement that we do all the time. That's what will make them more acceptable to people. And for that, there are solutions available in traditional control systems and optimization formulations. But again, we need to bring in humans to be in that design loop to help us reach the final movement behaviors that we want on the robots. And for that, with that, I would like to acknowledge my collaborators, my research colleagues, and the funding agencies. And that's all I have, and I'll be happy to answer any questions you have.
Any questions?
Yeah, I saw the Jacobian matrix. So what did you do with Jacobian with this regular? You did not do any control.
I did not do any controls, but the idea of Jacobian, I believe you mentioned here. The idea of Jacobian was to find the position, given the mathematical model, I wanted to find the position of my swing foot. So as a recall, I was mentioning this model of phase, where I have one foot on the ground and the other leg moving forward. Jacobian gave me the swing foot position. And I wanted that because I wanted to restrain the velocity of that point in horizontal direction and vertical direction. Because remember, I mentioned that as my swing foot touches the ground, it should not have any velocity upwards and downwards. It should just stay there. It should have a zero velocity. So Jacobian is what gives you the position from its mathematical model. Does that answer your question or not? So yeah, if it not helps, I can help you later. So what the last point is, when I define the mathematical model, I have an equation for this point. Now, if you want to find the velocity of this point, you have to multiply with the equation, Jacobian. Any other questions?
So I
Yes.
guess the question is, that E there is not the Jacobian, right? You're talking
is.
about the Jacobian of E.
No, it is the Jacobian.
Because that's just the Givens matrix, right?
That's what? Sorry?
The Givens, this is just a rotation matrix.
No, that is the Jacobian. This is my Jacobian of the swing foot position. I multiply that Jacobian with the angular velocities.
I guess
So-
the same, yeah, okay.
But yeah, rotation matrix has a similar structure as well. But
Yeah, it's the same.
yes. Yes, go ahead.
So I'm going to ask a devil's advocate question. I'm not suggesting this is true. I'm just trying to pick out where it is. So what's the benefit of having analytic models here? Because the parameters that you come out with at the end of, so the sample parameters that you come out with at the end, they're not going to be necessarily the ones that you use to drive the robot. I mean, ultimately, you really only care what it is that you need to drive the robot.
That's a good point.
So
I
if
mean,
you could get those from machine learning, would you need the analytic models?
Yeah, I think, so let me rephrase. What you're saying is, if I came up with PS and TL, the gait parameters, how I move.
Well, whatever it is that you need to control the robot.
Yeah.
So I don't know whether that would be
Mhm.
TL and PS, or whether you need,
So
there would
it's-
be as many motors as you need, right?
So are you saying if you give me U of T, or the input for my model through some other source?
Input for the robot.
For input
for
for
a
the robot,
particular robot.
do you need dynamics for that or no?
Do you need an analytic model for it? I'm not suggesting. I realise it's still useful to classify and so
Mhm.
forth. I'm just
Um,
curious.
There's always some percentage to which that will work. But analytical model, in my opinion, for at least simpler models, for which you can derive analytical models, it gives you a reasonable guarantee that this is how they will behave. But if you have machine learning based or some AI-based just parameters instead of analytical models, they will always have some percentage of guarantees that they will work in so scenarios. But they may break down in others. So, but if you have very well defined the problem, constrain the problem to be only for a specific scenario, yes, there will be no problem just going that way.
And I don't believe that analytic models are not useful. I'm just trying to figure
I get your point.
pick out the problem.
Yes.
Would there be similar research maybe in the video game industry, it would seem they should be interested in having their avatars walk in different gaits. I don't know, is there a similar state of the art? What are they interested in that's different from what you're doing?
I've not looked at them in detail, so I wouldn't know for sure, but yeah, I cannot comment on that.
I have a question.
Yeah.
So you are doing some control here, active control here.
I'm not doing.
So,
I'm doing an open loop control, I would say.
so basically, you are trying to move this mass, and then the robot basically react to that.
Yeah. Well, not exactly that. There a lot of things are just coupled, but I'm still controlling. I'm just moving these two things, and as a reaction of that, everything else is coming into place. So I can loosely say that, but that's not an exact statement.
Okay, fair enough. So the second part of the question is the type of robot that you said that you'll be needing seems a pretty straightforward design, right? The model that you showed us now in the slides with these legs doesn't look like very complicated, right? So my question is, how do you extend your current work, right, to a more complicated, right? Right now you have maybe like 3-4 degrees of freedom robot to let's say very advanced robot like this,
7 degrees of freedom,
right?
Yep.
So where do you think, how would your theory would fare in a complicated system like that?
I will have a more complicated dynamics here. Another thing will be calculating dynamics for that robot at each step, if it's actually satisfying or not. That will be time taking, so I will have to resort to some hacks I've made in the optimization, the robotics community. So I will look into those. Other than that, I've made an assumption. I've simplified the model to be a swing phase and a double or a strike phase. In their case, if the leg is different, that's a different phase. So they have a more detailed structure to them because the two legs are not exactly the same for them. So they have 2 swing phases for each leg. What I hope is the structure will remain the same. That I pick some gait parameters that I tweak around, and rest of the routine will be the same. I'll go over. I'll find some inputs that satisfy the walking constraints. Does that answer your question?
I mean, yeah, sure. The robot will be complicated, so the associated modeling and other problems will be scaled up. So my question is related to right now you are changing the mass, right, with your test. So that has, let's say, maybe 2 degrees of freedom of controllability you have. And you have right now maybe 3 or 4 capacity degrees of freedom, but when your actual robot has, let's say, 20 plus degrees of freedom, your input degrees of freedom is, I would say, not enough to control. So how would this?
Okay, now I get it. Okay, so that in a way is related to the choice of gait parameters. Here I picked this to be these gait parameters, but in their case, it doesn't have to be exact joint angle that I'm changing. It can be a more, I would say, a more coupled thing. For example, ZMP. I might just look at the ZMP movement, which again would be impacted by different joint angles. So it would be a major portion of the degrees of freedom. So it doesn't have to be in a single joint angle that I'm changing in those cases.
So you want, when you extend your model to such a complicated robot, you still expect that the degrees of freedom of the legs would be actuated, but you'll compensate for some degree.
Zoro, I think there's people outside waiting.
Yeah. All right. Thank you. So yeah, we'll take it.
Let's do that.
Discussion later on. But we have another talk right now. This is another faculty candidate. If you want to stick around, please do.
For software engineering.
Yeah, it's a software engineering candidate. Yeah.